I'm now going to define a few very new concepts to you: albedo, emissivity, and black body radiation. Before I do that, let's review the solar constant. The solar constant is the amount of energy that the Earth receives, and we can make good use of it, planning accordingly using this number. The intensity of radiation is inversely proportional to the square of the distance from the source. Now, if we know the intensity of the sun, or the light coming from the sun, and we know the distance from the sun, here it is, to the Earth, then we can work out easily what the amount of energy per second per square meter is, using the relationship intensity equals power over 4 pi r squared. Why 4 pi r squared? If you remember rightly, it's the area of a sphere. If we plug in the values of 1.5 times 10 to the 11 as the radius, and for power, 3.9 times 10 to the 26, then you can work out the solar constant easily. Now, as we mentioned before, the solar constant is only part of the story. We do get 1,380 joules per second per meter squared on average, but in reality the number is much less than that. There's all kinds of factors involved in why the number is less. Now, if we consider part of the radiation incident on the Earth is directly reflected back into space, and some of it is absorbed. The ratio of the total scattered or reflected power and the total incident power is called the albedo, and you can represent it as a percentage. So, the albedo, by definition, is the ratio of the totally scattered or reflected power and the totally incident power. So if we look at this diagram, which is really simple, the sun emits some light energy, or 1,380 to be exact. However, some of it is reflected. The ratio of this reflected to this incoming gives us the albedo. The Earth's albedo depends on many things, and it changes. And things that can change it, and this is important that you can quote some of these, we mentioned them before: the latitude, the season, and the weather. The latitude, because the actual incoming radiation would be less, because in some areas of the planet, the light reaching from the sun is not head-on, it's spread over a wider area. So that incident number, that 1,380, the solar constant, would be much lower. But then there are other things. The weather, for example, cloud cover, will affect the reflected radiation, although the incoming would be the same. Seasons, for the same reason we mentioned before with latitude. At certain times of the year, the Earth tilts, so some areas are at an angle, and so there's more spreading. The absorption properties of the area where light lands, is very important. Colour, white and bright surfaces have a high albedo. Why? Because white and bright surfaces mean that more light is reflected. From radiation, when we covered it a few lessons ago, the whiter or the lighter the colour, the more reflection you get. And the more reflection, the higher this top value. Snow has a very high albedo, almost 90%, while the albedo of the oceans is very low, between 5 and 10. The Earth's average albedo is approximately 30%. Now, as you can imagine, this is very, very relevant to the greenhouse effect. As we know from the greenhouse effect, the snow, or the areas with high amounts of snow, are melting. Those are areas which reflect more light, and if they start to melt, the albedo, the average albedo of the planet, will go down, which means that more heat energy will be absorbed, which is precisely what we don't want to happen. But we'll talk a little bit about this later.